Today we are going to have a module on clinical significance of protein and tissue binding of drugs. What are exactly the significance of this binding on the drugs? Myself Prashant Naik, Assistant Professor, Department of Pharmaceutics, NGSM Institute of Pharmaceutical Science, Mangalore. So what are the learning objectives? The learning objective is the significance of protein and tissue binding as compared to absorption, what happens, distribution of drug, what it happens, and tissue binding, apparent volume of distribution, drug storage, and elimination. So these all things we will learn today. Absorption. Absorption is nothing but the absorption equilibrium is attained by the transfer of free drug from the site of administration into the systemic circulation. And when the concentration in these two compartments become equal, following equilibrium, the process may stop. However, binding of unabsorbed drugs to plasma protein decreases the free drug concentration and disturbs such equilibrium. Thus, sink conditions and concentration gradients are re-established, which now act as a driving force for further absorption. This is particularly useful in case of ionized drugs, which are transported with difficulty. Distribution. In case of distribution, plasma protein binding restricts the entry of drugs that have specific affinity for certain tissues. This prevents accumulation of a large fraction of drug in such tissues and thus subsequent toxic reactions occur. Plasma protein binding thus favors uniform distribution of drug throughout the body, but its buffer function maintains equilibrium between the free and bound drug. A protein bound drug is particular does not cross the blood brain barrier, the placenta barrier, and the glomerular filtration. Tissue binding, apparent volume of distribution, and drug storage. A drug is extensively bound to blood components remain confined to blood. Such a drug has a small volume of distribution. A drug that shows extravascular tissues binding has a large volume of distribution. A tissue or blood component that has less great affinity for a particular drug acts as a depot or storage site for that drug. Example, RBC is a storage site for lipophilic compound tetrahydrocannabinol. Now we'll see relation between the tissue binding of drug, apparent volume of distribution. The first equation we know Vd equals to x by c, where x stands for amount of drug into the body, c stands for plasma concentration. If you take x on a side, the equation becomes x equals to Vd by c. That means the amount of drug of the body is equal to volume of distribution and concentration, plasma concentration of blood. So we can rewrite the things. Amount of drug in plasma equals to Vp by C in the plasma, Vd in the plasma, volume of distribution in plasma. So the amount of drug in extracellular tissue will be Vt or Ve by Ci. Now the total amount of drug in the body is the sum of that of the plasma and extravascular tissue. So Vd by C, volume of distribution, Vdc from the previous equation equal to Vpc plus Vtct, where Vd stands for apparent volume of distribution, Vp stands for volume in the plasma, Vt stands for volume in the extravascular tissues, and Ct stands for tissues drug concentration. So this is the exact equation we get after substitution. Then dividing the equation C by C, we can get Vd equal to Vp plus Vt, which is nothing but apparent volume of distribution, is nothing but the volume in the plasma plus volume in the extravascular tissues. Now, if we take T as common, F as common, and we say the fraction of unbound drug in plasma we have to find out is equal to the concentration of covalent drug in plasma, Cp, divided by total plasma drug concentration, C. Now, similarly, fraction of the unbound to tissues will be T by C by T by C by T, C by 1. Assuming that the distribution equilibrium and the unbound few drug concentration of plasma equals that the extravascular tissue C of extravascular tissue and C in the plasma equation can be combined and written as Ci by C Tn by Ta, T in plasma by T in tissues. Substituting the equation Vd equals to volume in plasma plus volume in the extravascular tissue, fraction of drug in the extravascular in the plasma divided by extravascular tissues. So it is clear that the greater the unbound drug or the concentration of drug in plasma, larger is the volume of distribution. Elimination. Only the unbound or free drug is capable of being eliminated. This is because the drug protein complex cannot penetrate into metabolized organs like liver. Large molecular size of the complex also prevents it getting filtered through the glomerulus. Thus, drugs which are more than 95% bound are eliminated slowly. That is, they have long elimination half life. For example, tetracycline, which is bound 65% and has an elimination half-life of 8.5% as compared to 15.1 hours of doxycycline, which is 93.9% bound to plasma protein. However, penicillin has short elimination half-life. This is because rapid equilibrium occurs between the free and the bound drug, and the free drug is equally rapidly excreted by active secretions in renal tubules. So this is the reference which you have taken from Shagil, Applied Pharmaceutics and Biokinetics, Brahmankar and Jaiswal, Biopharmaceutics and Pharmacokinetics. To summarize with the things, what we have learned is, we have seen what are the clinical significance, what exactly happens for the drug in case of absorption, in case of distribution, in case of volume of distribution, and then in the case of elimination, how the drug behaves. And we have seen the equations how to derive the volume of distribution in plasma extravascular tissues of bound and unbound drugs. So that's all for now. Have a nice day. Bye.